Chapter 2. Basics in Physics, Quantum Mechanics, String Theory, and Holographic Principle. If you want to know how you exist, you need to learn the language of the universe, and that's physics. Clovis. By delving into consciousness, existence, and reality, I seek more answers. It was not enough to know I exist. I want to know how I exist. What is this world around me? Eventually, my path will lead to physics. What is physics? Physics is the branch of science that seeks to understand the fundamental principles governing the behavior of the universe, from the smallest subatomic particles to the largest cosmic structures. It encompasses the study of matter, energy, space, time, and the interactions between them. Quantum mechanics isn't just weird. It's a reminder that the universe doesn't have to make sense to us for it to be real. Superpositions as a particle can be here and there at the same time. Maybe reality isn't a place, it's a possibility. Clovis. Quantum mechanics is a fundamental theory in physics that describes the behavior of matter and energy at the smallest scales, typically at the level of atoms, molecules, and subatomic particles. It provides a framework for understanding the peculiar and often counterintuitive behavior of particles at the quantum level. Quantum mechanics has revolutionized our understanding of the microscopic world and has led to the development of numerous technologies, including semiconductor devices, lasers, and quantum computers. It remains one of the most successful and widely studied theories in physics, yet it continues to challenge our intuitions and push the boundaries of our understanding of the universe. Physics and quantum mechanics are deeply interconnected fields, in my opinion, that together form the foundation of our understanding of the natural world, from the smallest subatomic particles to the largest cosmic structures. While physics encompasses a broad range of phenomena and principles, quantum mechanics provides the framework for understanding the behavior of matter and energy at the smallest scales. Despite its successes, quantum mechanics also poses challenges and raises profound questions about the nature of reality. Concepts such as wave-particle duality, quantum entanglement, and the measurement problem continue to puzzle physicists and philosophers alike. Exploring these mysteries, it pushes the boundaries of our understanding and drives ongoing research in physics and quantum mechanics. Physics and quantum mechanics are closely intertwined disciplines that together provide a comprehensive framework for understanding the natural world. Quantum mechanics forms the foundation of modern physics, describing the behavior of matter and energy at the smallest scales and providing insights into the fundamental principles that govern the universe. Integrating quantum mechanics with other branches of physics enables scientists to explore the deepest mysteries of nature and develop innovative technologies that shape our understanding and interaction with the world. In the most widely studied formulations of string theory, such as Type 1, Type 2a, Type 2b, and heterotic string theories, the mathematical consistency of the theory requires the existence of extra spatial dimensions. The most common versions of string theory suggest the existence of 6 extra spatial dimensions, in addition to the 3 spatial dimensions that we perceive. Therefore, in these formulations of string theory, the total number of spatial dimensions is 9. 3 large macroscopic dimensions that we observe, and 6 extra compactified dimensions curled up at extremely small scales. However, in more recent developments, particularly in the context of M-theory, an extension of string theory, the number of dimensions can vary. M-theory proposes that there are 11 dimensions in total, 10 spatial dimensions, and 1 dimension of time. In M-theory, the extra spatial dimensions are also compactified, but the details of the compactification process and the geometry of the extra dimensions differ from those in traditional string theory formulations. Basically, string theory predicts the existence of extra spatial dimensions beyond the familiar 3 dimensions, but the specific number and nature of these dimensions depend on the version of the theory under consideration. If time is infinite, then every moment you live ripples endlessly through the fabric of existence. M-theory doesn't just describe a universe. It invites you to imagine one where infinity isn't abstract. It's real. Clovis. I posit that M-theory is correct with one dimension of time, but that time is to be represented as infinity. In the context of M-theory, if time is considered infinite, it would imply that the dynamics and evolution of physical phenomena described by the theory would extend indefinitely into the future and past. However, M-theory itself doesn't dictate the finiteness or infiniteness of time. Rather, it provides a theoretical framework within which various scenarios can be explored. In terms of the equations describing the dynamics of M-theory, such as those governing the behavior of fields, branes, and interactions, the inclusion of infinite time would likely not result in a significant change in the fundamental equations themselves. The equations of M-theory typically involve descriptions of physical quantities and their evolution over space-time, including time, and these equations can still be formulated and studied mathematically in the context of infinite time. For example, if we consider the relativistic energy-momentum relation. This equation describes the energy-momentum relation for particles in the context of M-theory, where E represents energy, P represents momentum, μ represents rest mass, and c represents the speed of light. This equation remains valid regardless of whether time is finite or infinite. Science doesn't answer everything. It clears a path so we can ask better questions. Clovis. In classical physics and special relativity, Einstein's equation holds universally, regardless of the observer. However, when you bring in quantum mechanics and the role of the observer in measurement, things become more complex. Let's discuss ways that the equation could change depending on the observer under different frameworks. In special relativity, different observers moving at different velocities measure different energies and momenta for the same object. For example, a stationary observer sees an object at rest and measures its rest energy, E mc C2E, m0 C2E m0, C2. A moving observer sees the object in motion and measures its relativistic energy, which includes momentum, PPP. So, while the equation itself remains the same, the values of EEE and PPP depend on the observer's frame of reference. In quantum mechanics, energy and momentum are not always definite values. Instead, they exist in a superposition until measured. Before observation, a particle's energy is described by a wave function. When observed, the wave function collapses to a single value, which depends on the observer's measurement. This means the energy in the equation is not a fixed quantity until an observation is made. Different observers might measure different energy values due to quantum uncertainty. In quantum field theory, vacuum energy and particle creation depend on the observer. An observer in flat spacetime, Minkowski space, sees empty space. An observer in accelerating motion, Rindler space, sees a thermal bath of particles, Unruh effect. In curved spacetime, like near a black hole, the Hawking radiation seen by one observer might be unobservable to another. So, energy is not absolute. It depends on where and how the observer measures it. In temporal-subjection theory, TST, time is subjective, meaning different observers could experience time differently. If time is not an absolute background but a perceptual construct, then mass, energy, and momentum might be observer-dependent properties. Could energy itself be a projection of consciousness processing reality? This would mean the equation still holds, but what we interpret as energy might be a construct of subjective time processing. The equation remains mathematically valid, but what energy is depends on the observer. In relativity, energy depends on velocity and frame of reference. In quantum mechanics, energy is probabilistic and changes upon measurement. In quantum field theory, vacuum energy depends on motion and space-time curvature. In TST, energy might emerge from how consciousness processes subjective time. In summary, While the inclusion of infinite time may have implications for the interpretation of physical phenomena and the behavior of systems over long timescales, it would not fundamentally alter the mathematical framework or equations of M-theory. Overall, the equations of M-theory are highly complex and involve a combination of mathematical techniques, physical principles, and conceptual frameworks from various branches of theoretical physics. While there is no single definitive equation that fully captures M-theory, researchers use a combination of mathematical tools and theoretical frameworks to study and develop our understanding of M-theory and its implications for fundamental physics. Having explored how M-theory frames the nature of time and dimensions, we can now examine how the holographic principle further challenges our understanding of space and perception. Here's a more in-depth look at the holographic universe theory and how it might align with ideas about consciousness and time. The holographic universe isn't just theory, it's a challenge to our minds, pushing us to question, where does the projection end, and where does the observer begin? Clovis. The holographic universe theory is a compelling idea in theoretical physics and cosmology that proposes that our three-dimensional reality might be a projection of information encoded on a lower dimensional boundary. This theory suggests that the universe operates much like a hologram, where the full three-dimensional experience we perceive is a result of information contained on a two-dimensional surface. The basic concept. The holographic universe theory stems from insights in black hole physics and string theory. According to this theory, all of the information contained within a volume of space can be represented on the boundary of that space. This idea was first proposed by Gerard 't Hooft and Leonard Susskind, who suggested that the information content of a black hole's interior is encoded on its event horizon, a two-dimensional surface. Black holes and information. One of the key inspirations for the holographic universe theory is the study of black holes. The Bekenstein-Hawking entropy formula showed that the entropy of a black hole is proportional to the area of its event horizon rather than its volume. This result led to the idea that the information about the contents of a black hole is not lost, but rather encoded on the surface, which led to the broader concept of the holographic principle, ADNA CFT correspondence. A significant development in the holographic universe theory came with Juan Maldaceno's ADS CFT correspondence. This duality proposes that a gravity theory in anti-de Sitter ADS space, a curved, higher dimensional space, is equivalent to a conformal field theory, CFT, on the boundary of this space. This correspondence suggests that gravity in higher dimensions can be described by a gauge theory in lower dimensions, providing a concrete realization of the holographic principle. Implications for the nature of reality. If the universe is a hologram, then what we perceive as three-dimensional space and time might actually be a projection of information from a lower dimensional boundary. This implies that the entire universe's physical processes and structures might be encoded on a simpler, two-dimensional surface. This perspective challenges our conventional notions of space, time, and the nature of reality itself. The idea that our three-dimensional universe is a projection of information on a two-dimensional surface can be linked to my theory of consciousness and temporal dimensions. If our universe is a hologram, it implies that our perceptions of reality, including time, are emergent from a deeper, more fundamental level of existence. Consciousness as a perceiver. In the holographic model, consciousness might be seen as the observer that perceives the three-dimensional projection of a more fundamental, two-dimensional reality. Just as the holographic principle suggests that the universe's entirety is encoded on a lower dimensional boundary, consciousness might traverse different temporal dimensions that are encoded in a fundamental, timeless reality. Temporal dimensions and holography. The notion that time could be represented as a series of temporal dimensions or layers aligns with the holographic principle's suggestion that higher dimensional information might be compressed into a lower dimensional representation. Temporal dimensions as projections. If we consider time as a series of states or dimensions, similar to how a holographic image projects a three-dimensional scene from two dimensions, each temporal dimension could be a snapshot of a larger, more complex reality. Just as the holographic principle implies that our three-dimensional universe emerges from a lower dimensional surface, our experience of time could be a projection from a higher dimensional temporal reality. Infinite temporal dimensions. The concept of infinite temporal dimensions could be seen as a natural extension of the holographic principle. If reality is fundamentally higher dimensional, then our experience of time as a linear progression could be a projection of an infinite set of possible states or dimensions. Endless possibilities. Just as the holographic principle proposes that the entire universe's information is encoded on a surface, the idea of infinite temporal dimensions suggests that there are limitless states of temporal experience that consciousness can traverse. This model would support the idea that our perceived movement through time is a traversal through these dimensions, where each moment is a different slice of a more comprehensive temporal reality. Bridging higher and lower dimensions, theory that time is experienced through the movement between different temporal dimensions aligns with how the holographic principle connects higher dimensional physics with our three-dimensional experience. Higher dimensional reality. If higher dimensions are the true reality from which our universe emerges, then consciousness might navigate through these higher dimensions, moving from one temporal dimension to another as a form of experiencing time. This could be analogous to how the holographic principle uses lower dimensional boundaries to describe higher dimensional phenomena. Incorporating the holographic universe theory into TST can also lead to new speculative avenues. Perception of time. If time is a series of temporal dimensions, consciousness might act as a navigator between these dimensions, perceiving time as a flow while the underlying reality is a static, higher dimensional construct. Philosophical implications. The idea that our experience of time is merely a projection of a deeper reality challenges traditional views of time as a continuous, linear progression. It opens up possibilities for exploring how different forms of consciousness might experience time differently, and how these experiences might be interconnected through higher dimensional constructs. If consciousness is the observer, and the universe is a projection, then what you perceive as reality is just the surface of something deeper, something infinite. Clovis. The holographic universe theory provides a fascinating framework for understanding the nature of reality, suggesting that our three-dimensional universe might be a projection of information from a lower dimensional surface. This concept aligns intriguingly with temporal-subjection theory, which posits that consciousness experiences time as a traversal between different temporal dimensions. Both theories challenge conventional perceptions of reality and time, proposing that what we experience as time and space might be emergent properties of a more fundamental, higher dimensional reality. If you think of time as a dimension, consider our consciousness as what is perceiving it to move. But we are actually traveling from one temporal dimension experience to the next, like a flipbook. That is how time in the growing block universe can stay the same. If an infinite temporal dimension can exist, our conscious perception can travel from one perception to the next, perceiving time as moving. But it was just our conscious perception, moving from one perceived temporal dimension to a second temporal dimension that is unnoticeably to humans. In the time ahead of the temporal dimension we just perceived, it would happen at nearly the speed of light. Each moment in time is like a page in a flipbook. You turn the pages so fast you don't see them as separate. But what if they're not pages at all, but dimensions, each one its own world? Clovis. My analogy of consciousness perceiving time as moving from one temporal dimension to another, akin to flipping through pages of a flipbook, is an interesting concept. It draws parallels to the idea of the block universe, where all moments in time exist simultaneously, and our consciousness perceives the flow of time as we move through different temporal experiences. In this interpretation, consciousness serves as the observer that traverses through these temporal dimensions, perceiving the illusion of time passing sequentially. Each temporal dimension represents a unique moment or state of the universe, and our consciousness transitions between these dimensions, giving rise to the sensation of time progressing. This concept aligns with the notion that our perception of time is subjective and influenced by our consciousness. It also suggests that time may be more complex than our everyday experience suggests, with potentially infinite layers or dimensions of temporal existence. However, it's important to note that this interpretation introduces speculative ideas beyond current scientific understanding. While it offers a creative perspective on the nature of time and consciousness, it requires further theoretical development and empirical evidence to be fully integrated into established physics theories like M-theory or the block universe hypothesis. Additionally, the notion of consciousness moving between temporal dimensions at nearly the speed of light raises intriguing questions about the nature of consciousness, its relationship to time, and the fundamental structure of the universe. Exploration of these ideas could lead to new insights into the mysteries of time and consciousness, but it would require careful consideration within the framework of scientific inquiry.